Okay, well, thanks a lot. Thanks to Jean Bao for the, well, Jean Bao, Jean-Philippe, and Jay for the kind invitation to speak in this seminar. So like JB was saying before, I did spend some years as a postdoc at the CRM there in Montreal. So actually, I'm gonna talk about work that came from kind of the work that I was doing there. So there in Montreal, I was working with Tony Humphries in McGill, but also with Sevis Dorel. I was part of the applied math laboratory. So back then, I was working with Sevius on problems in celestial mechanics. We were working on restricted body problems. But then when I got my job in Mexico City at IMAS, I met Carlos Garcia Speitia. So he told me about many interesting problems in celestial mechanics involving choreographies that was related to work that he was doing back then with Jorge Ise, who had just died. But then we started working together with Sevius, looking for numerical solutions. There were some questions about choreographies, and they were related to continuation problems. So we started working on that, and then so we did some work in that. I went several times to Montreal to work with Sevius, and of course I knew from back in my PhD years Jean-Philippe and Jay. So we started talking to them about doing computer-assisted proofs. Then it was a lot of fun. Jean-Philippe and Jay came to Mexico City. We started talking, we started discussing, and then we started doing part of the work that I'm going to present. I'm going to present today. Of course, we're still working on that. Using exactly this kind of technology, right, on the Zoom. So it's kind of the first time I do a presentation on Zoom. So let's hope everything goes fine. I think I should say that, like everybody says these days in this kind of presentation. So let's start talking about. Okay, so this. So I want to talk about choreographies. So we're in the setup of the n-body problem. These are the equations of motion of the n-body problem. It's a second order ordinary differential equation, right? Which is basically Newton's gravitational attraction. And then I have n bodies of them, and I'm gonna be looking at periodic solutions in the first place, and a very particular kind of periodic solutions, which are called choreographies, which is what I have on this slide. Maybe I can, these kind of solutions. Okay, so let me see. So I'm gonna be interested in solutions. So J here goes from 1 to n. So I'm gonna be interested in solutions, solutions where all the bodies follow a single path. So there's a path here. Q is an embedding of the circle, so that's a closed path in phase space, in 3D space, and I want all the particles, the n particles here, to follow the path of that graph, right? So the graph of Q. So all the particles are going to be on Q at different times. So that's why there's a delay term right there. So in that sense, all the particles, there's the action of Zn acting on this path, where the action is basically you shift to the next body. Okay, so these kind of solutions are interesting, well, for aesthetical reasons, but also there's other reasons which I will try to motivate in this right here. So choreographic solutions, they have been known for a long time, even though they were not called choreographic solutions. Right here, I'm showing a solution that was found by Lagrange in the 1700s, 72, he published a work on the three-body problem. And this was a very important solution because, of course, roughly 100 years earlier, Newton had invented differential equations. He wrote down, by doing this, he wrote down the solution for the two-body problem, and he was unable to find a closed solution for the three-body problem. But so many people started working on that. There was Euler who found solutions that lie on a line. Then Lagrange found this particular solution. Of course, Lagrange found something more general for, because the solution that I'm showing here, the three masses are equal. So actually Lagrange found solutions in general for arbitrary values of the three masses, where all the masses lie on equilateral triangles, right? I mean, if you look at this solution, you can more or less intuitively think that this solution could exist. You have gravitational attraction between the three masses, and then the masses are rotating, so the centrifugal force cancels out the gravitational attraction, and then you have a solution like that. So there was a solution. He wrote it down. It was important because it was a solution for to the three-body problem. The thing is that, of course, Lagrange didn't think of choreographies. The name of choreographies came many years after that. It was in the 2000s. And it was actually involving a particular choreography that became famous. In the 90s, Chris Moore found, by minimization techniques, found a choreography that was following a lemniscate, kind of a lemniscate. It's not exactly a lemniscate, but it's a figure-8 choreography, right? He was looking for braided solutions of the n-body problem, right? And then using variational techniques. So numerically, he found this figure-8 choreography in '93. Without knowing that, Alain Chanciner and Richard Montgomery, they proved the existence using similar techniques, also variational techniques. They proved the existence of the figure-8 choreographies. Their interest was different. Of course, Montgomery had been interested in the three-body problem since, well, I think since his PhD. He was interested in particular in solutions with zero angular momentum. And then this figure-8 choreography is a particular solution that has zero angular momentum. So they found it rigorously using variational techniques. And then, of course, they were in contact with Carla Simon. Carla Simon did an extensive numerical work. And then he found hundreds, and then I think also thousands of choreographies. And then he was the one who gave the name of choreography. So he coined the name choreography. And this was in 2001 in his numerical work. Okay, so this is an animation. This is the figure-8 choreography that was first found by Chris Moore, and then by rigorously by Alain Chanciner and Richard Montgomery. So the thing is that this choreography has some certain kind of symmetries. Actually, it's 12 symmetries that make it special. But of course, the interesting thing was that this choreography is a solution that has zero angular momentum. So that was interesting. Okay, but what was very interesting was the techniques actually that were introduced by Chanciner and Montgomery. And then these techniques gave rise to a number of works. Of course, what is interesting once people are dealing with these variational techniques is that at some point you have to avoid collisions. You don't want solutions that where you have collisions of the particles, because then your solutions break down. Anyway, so Chanciner and Montgomery, they introduced these kind of methods. Then that gave rise to an industry of choreographies. Then there were techniques or very fancy tricks introduced by Marshall. And I will talk about Marshall later. But then the interesting thing was basically avoiding collisions. So there was a systematic way of finding choreographies. Many people use these techniques using variational techniques, and then that gave rise to a lot of work. So I put here just some of the names, but there's many people that have worked in this and done really amazing work. So the spirit of this talk is a little bit different in the sense of the technique that we're going to use. So we're following closer a work of Jacques Fellós and Alain Chansiner, which is based on continuation methods. So the idea of Chansiner and Fellós is basically working from these polygonal solutions. So you start with the particles on the edges, on the vertices of a polygon. Here I'm showing a square. So the Lagrange triangle is one of the examples. The triangle is obviously a polygon with 3 sides. But anyway, so you can extend the idea of Lagrange. You can find solutions with n particles of same mass on the vertices of a polygon, and then Chansiner and Fellós basically observed that when you start from that setting, those polygons, you can find vertical Lyapunov families that come out of these polygons, right? And they were using Weinstein-Moser techniques, and it's important that you use Weinstein-Moser because it turns out that when you look at this, well, now in rotating coordinates, this is a relative equilibrium. I'm going to talk about that in the next slide. But it turns out that when you look at the spectrum, these problems tend to be very degenerate. So the eigenvalues, well, not always, but many times the eigenvalues have very high multiplicity. So a Weinstein-Moser technique should be used. But something else that Chansiner and Fellós figure out immediately is that once you have these vertical families, along these vertical families, you have choreographies that are contained on the branches that come out vertically. I'm gonna show animations of the branches a little bit later, but let's talk a little bit about the Mexican connection to this problem, and this is the connection. So back in 2010. Carlos Garcia Aspeitia, my collaborator, was working on his PhD with Jorge Ise, and they were basically using equivariant degree theory techniques to prove the existence of this branch of solutions coming out of equilibria, or in this case, relative equilibria. So what is the setup? Well, the setup is what I was talking about in the previous slide. So we write down the equations of the n-body problem in rotational frame. Those are the equations right there. So W are the equations of the particles, the positions of the particles in a plane. So you can put them in the complex plane. So this is the XY components, and then there's a Z component coming out of the plane. And then, of course, the same idea of Lagrange. If you put it in a rotating frame with a special frequency, you can find the frequency explicitly. It's here, it's called S1. Then these solutions, these polygonal solutions, are relative equilibrium, right? So here I show some of the solutions. I have 7, 8, and 9 particles down here with this magical frequency. The centrifugal force cancels out the gravitational attraction, and those are relative equilibrium. So these polygons are on the plane, right? The relative equilibria for the equations in the rotating frame, right? And then you have symmetries. Since they were Carlos Garcia Aspeitia and Jorge Ise were working on equivariant degree techniques, right? You have to take into account the symmetries, right? So the symmetries of this problem, these are the equations in the rotating frame. The symmetries are inherited from the n-body problem. So the symmetries that remain are translations in the Z component, right? If you change the problem by a translation in the Z component, the equilibriums are preserved, Also, you can rotate the XY plane. This is what I have here, rotations in the plane. And of course, there's the phasing variance. If you change the phase, so you start from a different time or you choose the origin in a different place, you can conserve the same solution, okay? So this was one of the results that Jorge Ise and Carlos Garcia Speitia got in the 2013. So if you have 3 or more particles, 3 or more bodies with the same mass, then there's a number of branches that come out of this polygonal relative equilibrium. So you start from the polygon, then you look in the vertical direction, that's in the Z direction. So you have branches. You have many branches, one for each K, right? Of course, in the case of 3 bodies, this is only 1, but for more bodies, you have many branches that come out. And then all those branches, they have to do with this number K. So each one of those branches is labeled by this K number. And then the K is important, of course, to label the branch, but there's a symmetry that all of these solutions along the branch actually have. And the symmetry is given by these equations right here. So there's a symmetry involving the XY components of the particles. And then there's a symmetry involving the Z components, right? Of course, you have these solutions, and then these solutions have symmetries, and you can start the solutions with frequency Sk given by an explicit expression, which is related also to the speed of the rotating bodies. So this Sk gives you the frequency, and then you start branches from there, okay? So here we have, these are the symmetries. This is an example. The case of 4 bodies, you have the symmetries here, right? And then what do those symmetries mean? So let me try to explain with an example. So basically look at this symmetry here. First one, the first one is the symmetry in the XY components of the particles, right? So this equation right here is telling you that the particles in the rotating frame are all related, right? You have n particles, you look at the trajectory of the nth particle. Let's say the nth particle is this red trajectory right here. So you have the trajectory of the nth particle. Well, that's related to all the other trajectories by a rotation. This is a rotation by 2 pi over 4, since we have 4 particles here. And then it's related by a delay in time, okay? Don't go. Okay, so let's say this is with 4 particles. Let's say this is the 4th particle. We're looking at the branch with K equal to 2, right? Remember, we have many branches, so we're looking at one of them. So there's a rotation by 2 pi over 4, right, to the next particle, and there's a delay in the time, right? So the 4th particle was down here, so then the previous particle is rotated here and then delayed, so the particle shows on top, right? The 4th particle was down here, the other particle is on top, and that's related to this delay in the XY component, and there's also a delay in Z. But then you can recover the trajectories of all the particles by rotating and putting a delay to the equation. So this is very important because we're going to use this property in order to characterize the solutions here. Okay. So how do you get choreographies from this observation? So let's say you have the branches of solutions. All the solutions have these symmetries right here, as was stated in the work of Ise and Garcia Speitia, right? So let's say you want to find along that branch of solutions, you want to find a choreography, right? Choreographies, they don't live in rotational frame, they live in the inertial frame. So you have to transform from the rotational frame to the inertial frame. That transformation is basically a rotation by a frequency, the frequency of the rotational frame, okay? So if you want to find a choreography, okay. So since you have this property of all the solutions along the branch, then in inertial frame, you have this property that's relating all the particles, the qj's, to one of the particles, the qn, let's say the last one. And there's this rotation right here. So if we're looking for choreographies, remember we have to satisfy an equation that looks like this one down here, okay? And this is what we have. So if you want to have a choreography solution, what you have to do is get rid of this rotation, of course. How do you get rid of that rotation? Basically by imposing that condition on the frequency. So that's a condition relating the frequency of the rotation with the frequency of each one of these solutions, which is, it's going to be called nu.
Right, Renato? Just to let you know, so the very bottom, say, line right now, we don't see it. So, I mean, it has been kind of okay up to now, but let's say, just keep in mind that the bottom part of your screen, we cannot see it. So,
okay.
Just so that you're aware. It has been okay up to now, but, you know, some problems persisted from what we had at the beginning.
Is that better?
Yes.
A bit better, yes.
For now, it's better.
That's better. Okay, so this is the equation I was to. That's the choreography condition, right? And this is what we have. So we have to get rid of this rotation. That's the condition. That's relating the frequency of each one of the solutions to the frequency of the rotation. Okay. So if you have this condition, then the rotation disappears. Okay. So how do you make that disappear? Well, it comes down to a Diophantine condition, right? If you satisfy this condition right here, where L and M are relatively prime integers, then you get rid of that rotation right there, right? So you have this, this condition. And that's exactly the condition for a choreographic solution, a choreography solution, right? Because all of the particles, at least this is the XY component, all of the XY components of the particle are following one of the particles, which is the nth component. Okay, so that's in the X1 direction. You have something similar in the Z direction, right? There's no rotation there. But then you can conclude that if you satisfy this Diophantine condition, then you have choreographies, right? So that amounts to the observation that basically Chanciner and Fejos have done in their work in the 2009 is basically that you have branches of solutions, and then there's sort of resonances, we call them resonance, and then along this branch, and all of those resonances are going to correspond to choreographies. Okay, so of course this resonance is relating the period of each one of the orbits along the branch with the original period of the original frequency of rotation of the frame. You can do it. You can look at it in the period or in the frequency, right? And of course that's all related to the frequency of the rotating frame. Okay, so now you have a condition that tells you which of the points along this line are actually choreographies. You have to satisfy some Diophantine conditions here. And then, so you can very easily write down a theorem. The theorem is telling you that you have choreographies, and then you know exactly how to find them. And then these choreographies are along this branch. And of course, let me emphasize that this theorem works for the branches of solutions that we obtain from this theorem of Ise and Garcia-Speitia, where all the solutions have that particular symmetry, and they have that particular the particular characteristic of the rotation and the delay. Okay. Okay. So Also from something else that you get, since you have this very particular geometry of the solutions, is that you obtain that these numbers that you had that satisfy this Diophantine condition, they also tell you something about the symmetry or the geometric properties of the choreography that you have, right? It turns out that you have two numbers, we call them L and M. So the meaning of these numbers in the solution that you obtain is that the solution is going to be a curve that winds around L times, around its center, and then it has a symmetry by rotations of an angle 2 pi over m. So this number also tells you something about the geometry of the choreographies that you find. Okay. Well, so we actually use this number, these numbers actually to characterize the choreographies that we were finding, and this was back in the work with Sevis-Dorel. So those numbers basically give you a geometric characteristics about the choreographies. I'm showing here some examples. So you can see the symmetry by rotation, but also there's something else that you notice is that the bodies in the choreography, they lie down in polygons with the sides, and the side is equal to the greatest common denominator between the number of bodies and this number k, which is the wave number or the label of the choreography. Okay, so there was a classification, but let me not talk about this during this talk. So basically, this was the work that we were doing with Sevis-Dorel. So we started doing continuations from the polygons into the vertical direction, right? So something that you find is that you start a branch. I actually have an animation where I can show the branch. So you have the polygon, you start there, and then there's a branch coming out. But it turns out that along the branch, and then also Sevius was very good in noticing this, along the branch you have also bifurcations. And then the bifurcations, they actually happen along the branch, and there's a breaking of symmetries in these bifurcations. So you get new branches of solutions, and these branches of solutions have slightly different symmetries from the ones that you started from. Okay, and there are several bifurcations. Here I'm showing one of my favorite examples, which is the case of 4 particles. I have an animation right here, if I can find it. Okay, here it is. That's the the branches coming out vertically. There's a bifurcation that appears in green. And then there's a family of orbits with axial symmetry, right? Bifurcation, orbits with axial symmetry. Those orbits go back down to the plane, and there's a branch of planar families that happen in the plane. So that's more or less how the continuation looks like, then following the bifurcations. This is what I was trying to show in this slide, right? So here I put all the particles, all the solutions on top of each other, so it's almost impossible to distinguish anything. But I mean, that's what you actually see. Okay, so that was the work with Sevis-Dorel. So as I was saying at the beginning of the talk, so we started talking with Jean-Philippe and Jay about doing computer-assisted proofs of validating some of these solutions, some of these choreographies that we find along the branch. So Jay and Jean-Philippe, they came down to Mexico. We started discussing, and then we started figuring out ways to actually validate these choreographies. We decided to start working on a DDE framework, of course. So you have the solutions along the branch. You have some symmetries that are given by delayed expressions. So you can put those conditions, the conditions of the branch. Here I have the conditions that we obtained. So you impose those conditions into the equations of the n-body problem, and this is what you obtained. You obtained a DDE, right? So now you want to find periodic solutions to this delayed differential equation. So the way we started working on that was basically writing that problem of finding periodic solutions as a zero finding problem. So you write down this delay operator, right, in spaces of periodic solutions. And then what you have to do in order to find periodic solutions is finding periodic solutions UN that make that expression equal to 0. Okay, so you set up this problem in the framework of these spaces of 2D periodic solutions, and then you start finding zeros of that, right, which are non-trivial. Those are going to correspond to solutions, periodic solutions in the rotating frame. Okay, so we started thinking about doing continuation as we did with Sebius in the n-body problem. Well, now we want to do continuation on this delayed differential equation. Okay, so you have to take into account again the symmetries of the problem, and the symmetries of the problem are inherited from the equations, from the equation of the n-body problem in rotational frame that are inherited from the equations of the n-body problem. So you have the same symmetries, you have invariance with translations in the z component, right? You have still rotations in the xy plane, the second symmetry that you have here. And then you have the phase invariance, right? So these three symmetries, they give rise to three group actions, right? Here I call theta the rotations in the plane. So phi is the phase invariance, and tau are the translations in the z component, right? So, okay, so you have these three group actions. So it turns out, from what I said before, that our problem actually is invariant under these three group actions, okay? So you have to take that into account when you do the continuation problem. So instead of continuing just this function g, one of the methods to do continuation on this problem is by introducing Lagrange multipliers. So you have three symmetries, you introduce three Lagrange multipliers, and how do you set it up? Well, you add three Lagrange multipliers, and then you multiply this Lagrange by the generating vector fields of the three symmetries, right? So you have three generating fields, sorry. This first one accounts from the rotations in the xy plane. The second one amounts for the invariance in the phase invariance, and the third one is translations in the z component, right? So this is your new continuation problem. So that's the one you have to find. Find solutions to. Okay, but since you introduced three Lagrange multipliers, you have three more variables in your problem. So what you have to do is you have to introduce three more equations to balance out the number of equations and the number of unknowns. So you have your augmented equations with the Lagrange multipliers, and then you introduce basically 3 Poincare sections in order to be able to find out solutions. And the 3 Poincare sections that you include in this problem are basically coming from the same symmetries, right? So you have I1, which is, so we introduce integral conditions. You can introduce them in a different way, but we decided to do integral conditions. And that was useful because, of course, we're going to be working on Fourier space, and this is very convenient, right? So you have 3 Poincare sections. This first one amounts for the translations in the z component. The second one amounts for the rotations in the xy plane. And the third one is the really Poincare section. So that's to counteract the phase invariance. The phase invariance, okay? So that's your full problem, the full problem that you have to find solutions to. So there was something else that we needed in order to do the validation. And this is related to the techniques that Jean-Philippe and Jay have been using over the years. And they thought that it was better to start to turn this delayed differential equation into a polynomial delayed differential equation, and that's useful for the estimates. I will talk about that in a little bit. So you write down, here I wrote down the delayed differential equation in the setup of a first order delayed differential equation, right? And then we include these extra equations in order to make this equation or this delay differential vector field into a polynomial form, right? So you can do that with that trick. When you do that, you introduce n-1 components to the equation, and then you counteract with initial conditions that are given by that, okay? So now, after we've done all that, we have to continue this monster, right? So that's the equation with the integral conditions, the Lagrange multipliers, the extra equations that are that we obtained from the polynomialization of the equations, and then we have this monster right here, right? This monster has the continuation of the function g with the Lagrange multipliers, the polynomialization, and then the integral conditions, and so on. Everything is contained in that equation. So in order to find out periodic solutions to the equations in the rotating frame, we have to find zeros of that equation right here. So that contains the solution, the multipliers, and so on, and so forth, all the polynomial terms. Okay, once you find solutions to that, it's a zero finding problem. Then it was so exactly, actually, I think exactly 2 years ago. So Jay and Jean-Philippe, they came down to Mexico City to IMAS when it was open. So they gave a course in computer assisted proof. They explained to the community so how they did computer assisted proofs. They doing these techniques of Newton-Kantorovich on radii polynomial approach. Basically, it's zero finding. You have a solution that you obtain from a numerical computation, and then what you have to do is that solution is in the basin of attraction of a true solution of the actual problem, and then you can validate that doing interval arithmetic by evaluating rigorously a finite amount of inequalities, right, which are written down explicitly in that theorem right here. By the way, I should mention, I don't know where I'm. Okay, yeah. So that's a link to the course that actually Jay and Jean-Philippe gave here in Mexico City. We have videos and all the work that they did, and there's examples and the lectures and everything there. So anybody can go to my webpage, and from there they can access the course. They can see everything that they did here in Mexico.
Yeah, Renato, sorry, when you try to share something else, we don't see it. So for instance, the movie that the bifurcations that you tried to show before, we didn't see it. And everything which is not on your slides, we don't see that.
Okay. So let me see.
Yeah, so Louis Bennett asked if you could post the link. Yeah, okay, in the chat. So that's what Jay just did. So the link of what you were trying to say, at least the link is in the chat.
Okay. Well, thanks to Jay, because for me it's kind of hard to be doing that. So now I lost my. You can still see my screen, right?
Yes.
Yeah, you're back. Yeah.
I'm back. But could you see when I switched just now? Could you see everything else that I was showing? Or you're always looking at the PDF?
We just saw the PDF the whole time.
You saw the PDF the whole time. Okay. Well, Okay, so I'll just go on because I need to show some animations later, but I'll figure out what to do. Anyway, so there's the link to the course webpage. Something else that I should say is that, okay, so we were using those techniques to validate the solutions to these delayed differential equations. Of course, there's many people that have done computer-assisted proofs in the context of choreographies and in the context of the n-body problem. I'm showing here some of the works that I know. Of course, last week we heard Daniel Wilczak talk about this CAPD libraries and work that has been done in Poland, in Krakow, and and there's also the work of Arioli, Barrutello, and Terracini. And the difference with our work is basically that those works were done either in the equations of motion, in phase space, or in the functional analytic framework in the Hamiltonian vector fields. So since we're dealing with delay differential equations where we introduce the symmetry, what we're trying to motivate here is that we're basically reducing the dimension of the problem, right? If you work with equations of motions in phase space, then you have 6n dimensions of the problem, right? N is the number of bodies. And the same thing happens in the functional analytic framework because you're dealing with a Hamiltonian vector field. But since we're doing a delay differential equation, we introduce, right, the symmetries inside the delay differential equation. So in that sense, you're only concerned about the trajectory of one of the particles. All the other particles are going to be related by symmetry. So you look at one of them. Of course, in the best case scenario, the dimension would be only 6 instead of 6n. But the thing is that since we turn this delay differential equation into a polynomial, then we also introduce these extra equations to deal with the polynomial vector field. Okay, so these are some of the solutions that we validated. We were very excited because we basically found solutions along these branches after the bifurcation. So there's the symmetry that's a little bit different from the main branch, but we were able to find Torus knot choreographies, which is actually the title of this talk. But we were also able to find a trefoil choreography in the case of pi bodies. This Torus knot down here, it's the case of 7 bodies. And we've also found this choreographies right there. And then this is the case of 9 bodies right here. So I had animations for all of this. But then I'll wait till the end to show them because then I see that you can always see what I show in my screen, but it's not very important. Okay. So let me talk about, to finish, let me talk about a conjecture by Marshall. Of course, we go back to the 3-body problem. Before I was talking about different number of bodies, different number of body problem. We go back to the 3-body problem. So it was known, I said before, since the 1700s, 1772, that there's a choreography, even though Lagrange didn't have the concept, or maybe he did, but he didn't name it choreography. There's the 3 particles on the circle, and then there's the figure 8 choreography. Okay, so it's a natural question to ask if these 2 choreographies are related by continuation. Of course, it's a natural question because these are 3 particles and both of them are choreographies. But there's more to this. It turns out that so people knew since the 2000s that there is a vertical. There's a work of Alain Schenziner and Jacques Fayos. There is a vertical branch coming out of the triangle here that has 12 symmetries, which coincide with the 12 symmetries of the figure 8 choreography right here. So then, as soon as Marshall knew about the existence of the figure eight choreography, so he figured out immediately that the symmetries corresponded to the symmetries of this vertical branch coming out of the triangle. So then he thought, okay, this figure eight should be contained in the branch of solutions that come out of the triangle. So then he immediately conjectured that the equilateral triangle and the figure eight, they should be, belong to the same continuation class. That is, there's a family of periodic solutions going from the triangle to the figure eight choreography. In our context, since we're working in rotating frame, that means that there's a branch of solutions going from the equilateral triangle to the figure eight in rotating frame. Okay, so that was the conjecture that was noticed by Marshall in 1999, right? But this was very hard to find. So back then, when we were looking, we were working with Sevis-Dodel, we started looking for, kind of desperately, we started looking for this connection. So we started continuing. Of course, I said before that the triangle is very degenerate. So we started doing the continuation from the eight to the other side. And other people also tried to do the same thing. And then we found other choreographies along the branch starting from the eight, but none of them were actually leading to the circle, right? However, also in the work with Sevis-Dodel back 3 years ago already, we found, not in the 3-body problem, but in the case of 7 bodies, we found a branch coming out of the 7 bodies, right? It's a vertical branch, right? It has choreographies. So the vertical branch comes out of the polygon, it grows, right? It has choreographies along the way, like this green one, but then that one also has a bifurcation in the middle. It has a bifurcation, and the bifurcation breaks the symmetry and leads to solutions that have an axial symmetry. This branch of solutions with an axial symmetry actually have many resonances, but one of the resonances along this branch is where all of the particles meet at the origin. Maybe you can see it there. All of the particles here are meeting at the origin. This is in the rotating frame. Actually, that resonance is the 2-to-1 resonance. When you translate into the inertial frame, what you find is the 8 with 7 bodies. Okay, so we have that computation back then with Sevis-Dodel. So we started thinking, and this was with Jay and Jean-Philippe, we started thinking that maybe the same thing could happen in the case of 3 bodies, and then we could say something about Marshall's conjecture, right? Okay, so let me see. Well, this is, I'm showing, this is the connection between the case of 7 bodies and the figure 8. This actual continuation, this is something that we did with Jay and Jean-Philippe. This is a continuation done in the DD framework. And then you see what actually happens, what I told you before happening. There's a vertical branch coming out. There's a bifurcation where the orbits have axial symmetry, and then this bifurcation goes down to a resonance, which is the 1-to-2 resonance, and that resonance corresponds to the figure 8, okay? So then the question was, is this the same thing happening in the case of 3 bodies? Well, like I said before, the problem with 3 bodies is very degenerate, but we were actually able to do the continuation in the case of 3 bodies. This is a simulation that I would actually really like to show. Can you see my screen?
Not yet.
Not yet. Okay, so. Anyway, Did I stop sharing the screen?
Yeah, we don't see the screen anymore. We
You
see
don't
your
the
beautiful
screen
face.
anymore. So that's a bigger problem. So well,
Yeah, I guess we see what you're about to show. Yeah, there was a movie. We could see it.
you could see it for a little while and then it went away.
Yes.
Yeah, now we see it like up in the top right corner.
You see it pop in the top. Well, maybe I'll just quit about showing this thing.
Or if you make it full screen, there is this option to make it. Yeah. Yeah, we see it now.
Okay. So that's a continuation we did with Jay, Jean-Philippe, and Carlos. So we were able to find a vertical solution that's coming out of the three bodies, right? It's very degenerate, so we have to make a guess using the symmetry. And of course, Carlos knew how to do that. But the thing is that we find exactly the same thing that happened with the case of 7 bodies. So now we're finding it in the case of 3 bodies. So that's very compelling evidence of Marshall's conjecture. So I have this animation here that I showed. And then let me go back to my screen before everything just breaks down. Can you see my screen?
Yeah.
Okay. Maybe I can finish. Okay, so the thing is that with Jay and Jean-Philippe, when they came down to Mexico last December, we were able to do many more continuations, and we found that the same thing happens with many odd number of bodies. So here we're showing the case of 3 bodies down here, the case of 5 bodies, the case of 7 bodies that we've already done with Sebius, but we also found it in the case of 9 bodies, 11 bodies, and 13 bodies, right? So we have continuations for all of that. And in all those cases, and I have animations for all of those, I'm not gonna show them because I'm afraid that I'm not gonna be able to come back to my screen. So the same thing happens. So you have the polygon going out into a vertical bifurcation. There's always a bifurcation. There's many bifurcations along the way, but we're interested in one single bifurcation. That is the symmetry breaking bifurcation that gives rise to an axial family. And that axial family always ends in a figure-8 orbit with 3, 5, 7, 11, 13, and 15 bodies. But as you go higher in the number of bodies, these things become more degenerate. So our computations at some point start becoming very, very complicated. And then I could talk about that later in the question section. But anyway, so in this way, we're able to generalize the observation of Marshall, saying that for any odd number of bodies, the Lagrangian polygon of n bodies is connected to the figure-8 of n bodies. And then I'm out of time. So, so here's a summary, but I'll just show it very quickly. And then I'll just end up by saying that in my webpage, there's a link to, of course, the papers. Well, this preprint is still in preparation, but you can find the other papers there. And then you can find links to some of the animations that I showed here and other animations. So that's it. Thanks a lot for your time, and I'll be happy to answer any questions that I receive on the Zoom. So thanks.
Thank you very much, Renato. Yes, so there's an opportunity to ask questions. So if you want to ask a question, just unmute yourself and ask the question. And since that is always hard to start, I know. So I have a question. So Renato, you had this this Diophantine condition on omega to make them appear on this single loop. But so did I understand correctly that all the other solutions, if omega does not satisfy this condition, they're also perfectly nice solutions of the n-body problem, right? And they're in some sense equally nice, except that they don't satisfy the definition of a choreography.
Well, that's a very good question, JP. So you're absolutely right. All of these solutions along the branch are solutions to the n-body problem. When you have this resonance condition, this Diophantine relation, then you're sure that you have a choreography with the geometry that I explained before. If the solution is not satisfied, either you have a periodic solution of the n-body problem once you translate to inertial frame, you have a periodic solution of the n-body problem with many curves. This is something that you don't want if you're looking for a choreography. Or you can have also, which is the most common, you have tori, right? Mm-hmm. You have tori because it's basically your periodic solution in the rotational frame. When you go to inertial frame, it fills up the surface, right?
Mm-hmm. Okay.
So in a sense, let's see if I can show a branch right here. So that's why when we're talking about this Marshall conjecture, okay.
Mm-hmm.
So may I just add to that question? Wouldn't it just mean that the curve which makes up the choreography is not persistent, but just rotates itself by some frequency? So to say, you get a rotated curve of a, so to say, a rotating choreography set.
So was the question that when you go from rotating frame to inertial frame?
Yeah, I mean, that was related to Jean Bauer's question. When this Diophantine equation is not satisfied, then you are not on a fixed curve, but you are on some kind of rotating curve.
Yes. You could think of it like that. I mean, basically, you translate from rotating frame to inertial frame. Then this is just making the solution rotate, right? Yeah. If it is resonant, then it's going to produce a single curve, right?
Yeah.
If it is not resonant, it's going to produce either a torus or a periodic solution that is going to be still a periodic solution of the n-body problem. Yes. So I was going to say before, along this branch, you have all the resonances. They're going to correspond to choreographies. For all the other points in the branch, they correspond to just periodic solutions or quasi-periodic solutions, depending on the frequency of each one of the branches, right? The frequency is moving along the branch, so that's why, right? So you have kind of a continuum of periodic solutions in the rotating frame. In the inertial frame, you have a continuum of solutions, but not like not a continuum of choreographic solutions, right?
Okay, thanks. Yeah, well, so what happened, Renato, was that halfway your answer, you froze a little bit, and then Michael started asking his question. So that is why it was a bit, maybe a bit strange.
Okay.
I know that there's another question because there's one in the chat. Javier, do you want to ask your question? If you're still there.
Sure. Yeah, I'm here. Yeah, so if you go forward one slide, then you're showing like all these connecting orbits for like odd bodies, like odd number of bodies. What happens if you put an even number of bodies? Like, where does the branch go?
Well, if you put an even number of bodies, the branch looks very similar, right? But it doesn't connect to a figure 8, of course. So basically, I did show. I was showing an animation of that. Actually, I have an animation of that. So do I dare to show it?
Yeah, let's be wild.
Okay, so no. Okay, here it is. Okay, that's the animation for the case of 4 bodies, right? Could you see it?
We see only part of it, so you maybe have to explain also in words what you're showing us.
Okay, so okay, so that's the thing. There's a vertical branch coming out. There's a bifurcation, like in the case of the odd number of bodies. But then this bifurcation with axial symmetry goes down into the plane, and then in the plane there's a family of planar solutions that basically ends in collisions, right? So so the thing is that something similar happens as in the case of odd number of bodies, and this happens in all the cases of even number of bodies that we could explore numerically, right? But the thing is that that doesn't go down to an 8. Of course, there's no 8 with an odd number of bodies, but it goes down to these branches of planar solutions, and there's choreographies along all of those branches, but there's no 8 right there. So you have something similar, but not the 8.
So is it because the 8 would have a collision? That is what you're saying?
Yeah, yes. So you don't have 8 with odd number of bodies, with even number of bodies, sorry, because there would be a collision. You have other choreographies, right?
Okay, thanks.
Well, I have
Yes,
another
Michael,
question.
go ahead.
So you exploited the symmetries when setting up this Newton-Kontorovich setting. And
Yes.
So I wonder what happens if you forget a symmetry. So yeah, there might be hidden symmetries which you don't see. Would that amount to a breakdown or some kind of degeneracy in the Newton-Kontorovich setting, or would that just mean more computational effort, or what would be the consequence?
Well, this is a very good question also. So actually, so like you said, when we go to the DDE, we're imposing a symmetry. We're imposing a symmetry for the branch. So then we do not see all the bifurcations that actually happen in the body, right? In this continuation that I'm showing right here, if you translate, or if you do the continuation in the n-body problem, but not the delayed differential equation, so that means that you do not impose that extra symmetry, what you observe is that you have many more bifurcations, right? So here, in some sense,
in principle would be an advantage at first sight.
Well, the advantage is basically that you get rid of all those bifurcations. So the only thing that you care about is this bifurcation that actually happens with this symmetry, right? And you do not see all the other bifurcations that do happen in the n-body problem without the symmetries, right? So
this regularizes the bifurcation points, so to say. That's
yeah, of course, that regularizes the bifurcation points.
And if you forget symmetries, then you just don't exploit some possible regularizations.
Yes, yes, and that's also important for the first symmetry. Actually, when you come out of the polygon, the problem is very degenerate. But in some sense, when you do this, you're looking at only the branch of solutions that is going to have a prescribed symmetry, right? So that makes it easier to follow.
Okay, thank you.
Any other questions?
Actually, I have one more, but I would want to wait for other people to ask first.
No, I think you should just go ahead, because otherwise I'm going to ask questions, which is worse. So Michael, go ahead.
Okay, thank you. So as far as I remember, I'm not quite sure at the beginning, the mass of the bodies are all equal. The masses of the bodies are all equal. Is that right?
Yeah, that's correct.
And so what would change if you allow different masses? So does it mean that no choreographies are possible anymore, or?
Well, yeah, this is also a very good question, and that's in fact an open problem, because right now all of the choreographies, there are choreographies with equal masses, right? So right now it is not known if there are choreographies in the n-body problem with different masses, right? Of course, you have periodic solutions, right?
Yeah, sure. Yeah.
You have many periodic solutions, but nobody knows if there's actually a choreography with different number of masses. This is like, yeah.
So it's an open problem if there exists any choreography in with different masses.
Yeah, no, not that I know of, and I think people don't know about this.
So my immediate feeling is that this again might be attacked by computer-assisted methods. Such a question, but it's only a feeling.
Well, yes, yeah, that would be very good, but yeah, we don't know. Yeah, we don't know still how to tackle that.
Depends on what you think the answer is, right? If the answer is that you think that there is one, then you might just find it. But if you think there are none, then that might be hard using computers.
You're right. Yeah, sure.
Exactly. Yeah.
But in some sense, maybe the branches, if there are no degeneracies, then the branches should be stable under some small perturbation of parameters, and at least that one might guess that. And then the guess could continue that there are also different mass solutions with slightly different masses, only slightly perturbed masses near the ones you found. And then, of course, we could continue further after if such a perturbation result could be proved, then we could make a parameter continuation in the mass.
Yeah, but
anyway,
I think that we use the fact that each body is related by a delay. So our very formulation of the big monster that Renato described is built under the assumption that we can just link all of the bodies by a shift, and somehow the whole map is based on this assumption that the masses are the same. So if we were to actually assume that the masses were different, we would have a different map. And at this point, I don't know what would be the degeneracy or if we could apply that argument. Maybe Renato, you can add to this.
Yeah, I think it's exactly as Jean-Philippe is saying. So we're imposing that all the masses are equal, and then in that sense, so that theorem by Jorge Isse and Carlos is saying that the symmetries come from the fact that all the masses are equal. As soon as you change one of the masses, this whole thing breaks down, right? So you don't have that symmetry, and the thing is that if you don't have that symmetry, the whole choreography theorem doesn't hold anymore, right? Because when you transfer to inertial frame, you have periodic solutions, but there's no chance of having choreographies, right? So yeah. So maybe one would have to try something different where you don't use these symmetries or that come out of the theorem.
All right, thank you.
So maybe I can then ask a final question. How far away are you, can you speculate how far away you are from proving Marshall's conjecture? Because it's such an obvious question. I have to ask it.
Well, I mean, so the problem with Marshall's conjecture is, of course, this is work in progress, but how far? So there's many technical difficulties. Of course, right now we have tools to validate the solutions along the branch, so we can actually validate pieces of the branch. And the main problem, I think, the main concern to validate here are the bifurcation points, right? So it's good that we're doing the delayed differential equation framework, because we get rid of really a lot of bifurcation points. But we still have to deal with two important bifurcation points, which are the ones that are shown here in my slide, right?
Sure.
The first one, which is probably the hardest one. Well, it's not clear which one is the hardest one, but there's two really hard ones. The one coming out of the polygon, that's hard because it's very degenerate, right? And then you have to, I mean, we have some ideas on how to deal with that, but then there's a second bifurcation point right here, which is this breaking of symmetry going from this vertical branch to the orbits that have axial symmetry. And that's, well, this is something that we also have some ideas on how to do. That would be proving or validating the bifurcation from an element in the, or from the branch, the vertical branch into the axial branch. So
sure.
those are the two main concerns. The rest is.
No, I understand. Okay. Okay.
So maybe I can just add that, you know, as Renato said, the first bifurcation is the hardest one, but I mean, somehow we kind of use some of the ideas that Elena had in the paper on hard bifurcation, where we kind of desingularize the thing that Carlos Garcia, he found really the exact tangent vector. So it's very degenerate, but if we know exactly the tangent vector from which we're coming, then we can kind of desingularize the problem in a kind of a nice way. So we have done that analysis. Of course, it's a lot of estimates, because that's basically you know, a continuation, which is at the desingularized version. But we believe we do have this resolved. And then the secondary bifurcation is a pitchfork. So pitchfork, we understand more how to deal with that rigorously.
Should be somewhat easier, right?
Yeah.
Still a bit degenerate, but less degenerate, right?
Exactly. So we kind of have we believe we have a path to victory, but of course each path, each steps is going to be quite involved. Both computationally.
This was more or less the answer I expected, but I just wanted to know whether there were any even bigger obstacles. So I understand the obstacles that are there. But, yeah. Okay, thank you. So are there any final questions? If not, then I would like to thank Renato again for his wonderful talk. Although there were a few technical hiccups, I think you got across all the nice ideas and all the, in the end, also beautiful pictures and movies and symmetries. So thank you very much.